We just saw the definition of a positive semi-definite kernel, and we've seen a whole bunch of examples of these things. When we looked at all those examples of Gaussian processes, each of them had its own positive semi-definite kernel, or covariance function as we referred to it in that context. So next we're going to start taking a look at how to construct a positive semi-definite kernel. And it turns out that inner products are in some sense a canonical form of positive semi-definite kernel. So the very first example, way back up here, the very first specimen of Gaussian process that we examined was this random planes Gaussian process. And this one was just when we took S to be d-dimensional real space, this vector space, and we defined our kernel to be x transpose y, just the dot product of x with y, or in other words, the inner product of x with y. So if you don't know the term inner product, an inner product is just a generalization of the dot product to a more general form of vector space called a Hilbert space. Now, the dot product in d-dimensional real space is an inner product, and d-dimensional real space is a Hilbert space. And the really nice thing about Hilbert spaces is that our very sort of intuitive geometric notions about d-dimensional real space, most of those intuitions also apply to Hilbert spaces, and that makes Hilbert spaces just very, very nice to work with. Maybe a little later in this video, I'll give you a little example of a easy Hilbert space to get your head wrapped around. Okay, so our first example along these lines is the kernel defined by taking the dot product of x with y, and here S is Rd. Now, in a little bit, we're going to prove that this is in fact a positive semi-definite kernel. But first, let's look at a couple ways to generalize this. So one way would be to, instead of just taking the dot product of x with y immediately, we could first take some map phi of x and take the dot product of phi of x with phi of y. So here, S would just be some arbitrary set, S arbitrary, and phi would just be some arbitrary function from S to Rd for any Rd. And this is just the dot product on Rd. And the same proof that we will give for this number 1 to show that it's a positive semi-definite kernel or covariance function just generalizes immediately to this case. And now we can generalize one more time here to the following kernel, the following covariance function. We can take the inner product of phi x with phi y, and here S is again some arbitrary set, arbitrary, and phi now is a function from S to a Hilbert space H. So H is a Hilbert space here, and so I'll say H is a Hilbert space named after David Hilbert with inner product denoted by this parentheses with taking 2 arguments. So this is how many people write the inner product this way, but another way in which people write the inner product, which you will very often see, write an inner product, is in this way with these angled brackets. But that just means the same thing as the other way. I like to write it the other way mainly because I'm lazy and it's easier to write parentheses than brackets. But the brackets are the angle brackets are actually preferable in some sense because this is a little bit ambiguous because it looks kind of like a tuple. So I promised I would give you a little example of a Hilbert space. If you don't know what a Hilbert space is, well, of course, Rd is a simple example, but maybe the first non-trivial example to get your head wrapped around is little L2. little l2. So little l2 is the set, it's the space of all, maybe I'll use A, all infinite sequences, AI, such that the sum, so I is a sequence A1, A2, A3, and it's all those sequences such that the sum of the squares is finite. And here the A's could be, you could take them all to be real valued, or if you took them to be complex valued, that would be a slightly different space. But either of those you might refer to as little l2. Usually you think of it as the complex one, but you can think of them as real valued for now. And the inner product on little l2 is the sum, the infinite sum, AI, BI. And if it's real valued, it's just this. And if it's complex valued, if these AIs are in the complex numbers, then you put the complex conjugate over BI, but not over AI. So this is the inner product. And of course, the complex one specializes to the real case because the complex conjugate of a real number is just itself. So this is the inner product, and you can define the norm in a Hilbert space to be, so the square of the norm is the inner product of an element with itself, and that's of course just this original thing here. That's just this sum, this infinite sum, the sum of the sequence, the sum of the squares. And you would take the square root of this, and that would define the norm. And this is a generalization of the Euclidean norm. So of course you'll recognize that this is just a direct generalization of the Euclidean norm, because in RD, this just becomes the dot product of this becomes the dot product of A with B, and this becomes the dot product of A with A, which is the norm squared. Okay, so I just wanted to give you that little I think the first Hilbert space that you want to think about to sort of cut your teeth on and understand what a Hilbert space is. So this is a very, very nice little Hilbert space. Okay, and I wanted to mention this more general form, even though probably most people aren't familiar with Hilbert spaces. I wanted to mention this more general form because of a beautiful theorem called Mercer's theorem. ... Mercer's theorem. Mercer's theorem says that under fairly general conditions, any positive semi-definite kernel can be represented as an inner product in some Hilbert space. In other words, any positive semi-definite, under certain conditions, any positive semi-definite kernel, for any positive semi-definite kernel, there exists some Hilbert space H and some map phi from your set S to H, such that the inner product of phi x with phi y equals your kernel. So that's a very nice theorem to have, because inner products are just super, super nice to work with. They make life very easy. Whenever you've got an inner product on your hands, life is good. And that's why Hilbert spaces are so nice. You should not be intimidated by Hilbert spaces at all, because they're just very, very nice to work with, because they have this wonderful inner product structure. Okay, so now let's prove number one. Let's prove that this is in fact a positive semi-definite kernel. So let's prove this. Well, how are we going to prove it? So we need to remind ourselves what the definition was. We need to show, so we have our k, it's the dot product of x with y. And we need to show that for any sequence x1 up to xn, these are going to be vectors x1 up to xn now, the matrix obtained by taking the ijth entry to be this is symmetric positive semi-definite. Okay, so let's check that. Let's check. So we need to let, following that prescription, let x1 to xn be in Rd. And we form the matrix C, and this entry Cij is kxi xj, which by the definition of our kernel, we're looking at this one here, is xi transpose xj. And now we want to show that C is positive semi-definite. Symmetric, well, so first let's see that it's symmetric. That's obvious enough, because if we were to switch I and j, then we just get back the same thing. The inner product of xi with xj is the inner product of xj with xi. So that's simple. And now we need to show that C is positive semi-definite. So in order to do that, we need to say that for an arbitrary vector u in Rn, that u transpose Cu is non-negative. So in order to do this, we can make a very simple proof of this fact by using, so let me maybe write down what we're trying to prove, that non-negative. We can make a very simple proof of this by using the structure of C here. So I claim that C can be written as A transpose, where A is the matrix x1 transpose down to xn transpose. Those are the rows of A. So let's say n by d matrix. And so if you take this A and you multiply it times A transpose, then the ijth entry is going to be xi transpose times xj. And that's exactly Cij. And now, if you're very familiar with your positive semi-definite matrices, you will immediately recognize that this, I mean, you could stop right here, because in fact, every matrix that can be factored in, every real matrix that can be factored in this form is positive semi-definite. And the reason why is very easy to prove. So let's prove that. So we let our u be in Rn, and we need to prove that this is non-negative. So let's just plug in this representation. U transpose A transpose U. And we can transpose this left side if we, this is the same as A transpose U transpose times A transpose U. And what is this? This is just the dot product of A transpose U with A transpose U. So this is just the norm of A transpose U squared, the Euclidean norm. And the Euclidean norm is always non-negative, so therefore this U transpose Cu is non-negative, and therefore C is positive semi-definite. And that shows that this kernel K is in fact symmetric, or is in fact a positive semi-definite kernel, and it's symmetric, of course, also, or this one here. And the proof that I just gave just immediately generalizes to this. And there's a not much harder proof. If we had written out actually the details of what this means, what this what this operation means, then the same proof actually, with very minor modifications, generalizes to show that in fact this K here is also a positive semi-definite kernel. You just write out the sums instead of using matrices, and the same proof, basically the same proof applies. So there's nothing fancy going on in showing that this is in fact a positive semi-definite kernel.